this video, we're going to take a look at two more examples of complex roots. And the first one is going to be pretty short, and it's very similar to something that we've already done. In fact, you might be able to do it in your head without even doing any of what we do here. So it's going to be y double prime plus 9y is equal to 0. And there are no initial conditions, so it's just going to be a general solution that we find. We can write this as, we can find the characteristic equation, which is r squared plus 9 equals 0. From here we know that, well, you can do all the work, but r will equal plus minus 3i. And if you remember the form that we wanted r1 equals lambda plus mu I, r2 equals lambda minus mu I. Over here, well, it's just plus 3i and minus 3i, which means lambda is equal to 0 and mu is equal to 3. We can dump this into our long formula, right? So c1 e to the lambda t, lambda is 0, so that's just going to be e to the 0, which is 1. Then we have cosine of mu t, so cosine of 3t. Then over here we have c2, some other constant. Sine, e to the lambda t, lambda is still 0, so that's going to be e to the 0, which is 1. And then we have sine of mu t, mu is still 3, so it's 3t. c1 cosine of 3t, c2 sine of 3t. Again, these are constants, we can't actually find them until we're given initial conditions, which are not given over here. And this makes perfect sense. If you were to plug this in and check it, you can see that it will satisfy that exactly. Remember, you can also work similarly to what we did in the beginning. When we had just y prime plus y equals 0, we knew that one solution is sine of t. We knew one solution is cosine of t. And if you think about it, to go from y to y double prime, you're taking two derivatives. So the coefficient in front of t in either of these will be squared. So over here, when it's sine of 3t, the first derivative will become 3 cosine of 3t, and then it will become negative 9 sine of 3t. So it goes from 3 to 3 squared over the process of taking the two derivatives. So that's why we get the 3. That should make sense given the 9 and the 3. This is just a pretty simple example though. Basically all we did, all those other tricks are more kind of gimmicky, you might say. All you need to know is that you find r, you write in terms of lambda plus mu I, lambda minus mu I, plug them in, and that's it. We're going to take a look at another one that uses the exact same process, but it's a little bit more long-winded. And there's, I think there are also initial conditions in this one. Okay, no initial conditions in this one. It looks very simple, but the answer won't be as neat. I'll just warn you. So this is what we're given. What we do, first thing we do is find the characteristic equation. So r squared plus r plus 1 equals 0. Find the roots. We can use the quadratic formula here. It will be negative 1 plus minus the square root of b squared is 1 minus 4 times 1, so minus 4. This is just 3, negative 3 divided by 2. So this is negative 1/2 plus minus I root 3 over 2. Our form is lambda plus minus mu t, right? Oh, sorry, mu I, not mu t. Mu t will come in the sines and cosines in our solution. So what does this tell us? Well, lambda is just equal to negative 1/2. Mu is equal to root 3 over 2. That's all we need. It's actually not a difficult question. It's just the numbers are a little bit messier than they were before. And to find it, well, it's c1 e to the negative t over 2, and then cosine of root 3 over 2t, plus c2 e to the negative t over 2, and then here we have sine of root 3 over 2t. So that's it. This is going to be our final solution. Remember that because there are no initial conditions, we can't find c1 and c2, but you should still keep them. And if you want, you can go ahead and do the Wronskian. It's not, I don't recommend doing it. Well, you can if you really want to practice. What you would do is take this as y1 e to the negative t over 2 cosine of root 3 over 2t. y2 will be e to the negative t over 2 sine of root 3 over 2t. You want to find y1 prime, so that will be the derivative of this entire thing. You want to find y2 prime, which will be the derivative of this entire thing. And then you want to put that in that big determinant, evaluate the determinant, and you'll see that it's not equal to 0 at any point, and then you can verify that this is that this and this form a fundamental set of solutions, and this is a linear combination that encompasses all possible values, all possible solutions. So that's it for complex roots. In the next video, we'll take a look at repeated roots, which is the last thing that we need to kind of complete our exploration here. And then after that, we're going to explore what happens when this 0 changes into something else, when it's no longer a 0 and becomes non-homogeneous, right? Homogeneous means the right hand side is 0. In a non-homogeneous thing, you'll have some other function over here, and that'll make things a bit more complicated, but all of this is still very useful, and you'll see why. Thank you.